In this video, we're going to be exploring exponential notation as well as the properties of exponents that we see when we look at expressions containing exponential things. So let's go ahead and take a look at some patterns that show up anyways and see if we can make a conjecture as to why these things happen the way they do, while at the same time exploring what exponential notation is. So we say, how many factors are there in the product 2 to the third power times 2 to the fourth power? Now this is an interesting question. Once we find the answer to this, we're going to use that answer to write that product right here as a single power of 2. 2 to the something represents this thing here. So let's go ahead and start with exponential notation. When we refer to exponential notation, we're saying something is being taken to the power of something else and is turned into some answer here. So I'm going to refer to these using vocabulary here. We say this is my power. The thing that the exponent is attached to is the base. I want to be really clear on this. And then we say then this thing up here is the exponent. That's the actual thing right there that we call the exponent, okay? And when we write 2 to the third power, what we're really doing is we're saying this: 2 to the third power is equal to 2 times 2 times 2. In other words, what we're saying is it's a product with itself, and this exponent up here, really, this is telling us the number of factors that were in this product. So there are 3 factors of the base in this product. And we would get 8 in this case, okay? So we would get 8 for 2 to the third, and 2 to the fourth, we'd have to add in another 2 right here, and we get, instead of 8, we get 16. But we say 2 to the third power times 2 to the fourth power. What I really wanted to do is represent it this way. We say 2 times 2 times 2, 3 factors of 2, times 4 factors of 2. And what we can see already is this. Because these two expressions have the same bases, fact is, this was just telling me I have 3 of these, and this says I have 4 of these. Why couldn't we just write this as 2 to the power of 7? And so the pattern that I want to pick up on here, and we're going to look at this in more detail in these next examples, but is this. You know, when we multiply two things with the same basis, what can we do with their exponents? I notice I had a 3 here, a 4 here, and I got 7 for a response. So maybe my conjecture is this. Maybe I sum them, okay, and we'll talk about why. But it says write each product as a single power of 2 by counting the factors of 2. So what I want to be able to do is this. Instead of having to write this out 2 times 2, or 2 squared times 2 to the fifth, which is 2 times 2 times 2 times 2 times 2, 5 factors of 2, why don't we just go ahead and start to see that if I have 2 here and I have 5 here, then total I have 7 2's. So this would be an equivalent expression. This 2 to the second times 2 to the fifth would be the same thing as if we said 2 to the third times 2 to the fourth. We get the same response. And the same thing here, we say 2 to the first times 2 to the sixth. We must have 7 total factors of 2. So all of these are different ways of saying the same thing. I'm going to put my answer for C on this side. We say 2 to the third times 2 to the sixth. Well, I've got how many total factors here? I've got 9 total factors there. And 2 to the fourth times 2 to the fourth, interesting, we get 2 to the eighth. Okay, so without having to write all that out, let's see if we can complete this equation here. But we say two things that have the same basis. I want to be clear on this. These could have been 3's or 4's, or the Greek letter pi that represents 3.14, 159, and so on and so forth. But we say as long as they have the same bases and we multiply them together, what we're seeing here is that we are summing the exponents. So we get 2 to the m times 2 to the n is what this should say. So I'm going to rewrite this. 2 to the m times 2 to the n is equal to the 2 to the m plus n, okay, where we add the exponents. And notice this stays the same. The base stays the same, okay? So this was looking at products of things with the same basis. When we multiply stuff with the same basis, let's go ahead and take a look at now. Up here it says write each quotient, which is a division problem, as a single power of 2 by first writing the numerator and denominator in expanded form. So for example, if 2 to the third power, then we'll change it to 2 times 2 times 2, and then we'll cancel out common factors. So let's take a look at this first one here. It says 2 to the third over 2 to the first. Technically, what this means is I have 3 factors of this base up here and 1 factor down here. And by cancel out factors, what I mean is, this 2 and this 2 would cancel out and become, say, 1's. But I get left with 2 to the second power, essentially. So 2 to the second power. What we're trying to do is look for patterns here that would allow us to go from this initial statement to this terminal statement without having to go through this in-between stuff. So let's see if we can come up with a pattern on this next one. We say 2 to the fifth, so we have 5 factors of 2 up here, and 2 factors of 2 in the basement. And if we were to cancel out 2 of these with 2 of these, then we'd be left with 2 to the third. So we say, okay, well in the first one, I have 2 to the third over 2 to the first. These have the same basis. I'm dividing two things with the same basis. And then cancel out 1 on top and bottom. Essentially, we were left with 2 to the 3 minus 1, 2 to the 2. And then over here we see we have 2 to the fifth over 2 to the second, and I canceled out 2 2's top and bottom. So these two essentially canceled out with 2 on the top and left behind 3. But what we really did was we took 5 minus 2 to get this 3. So when I look at this next one, I say 2 to the seventh over 2 to the third, without having to write out 7 2's and 3 2's and canceling out 3 of them, what I could say is I really get this. I get 2 to the 7 minus 3 power, which really is 2 to the fourth power, and we could see that we get that when we write it out. And likewise here, we say 2 to the 6 minus 2, when I divide two things with the same basis, I keep seeing that I subtract the exponents. So these patterns keep showing up over and over again. We want to kind of generalize them. So we say 2 to the m over 2 to the n is 2 to the what? We just saw here when you divide two things with the same basis, you do the exact opposite of what you would do is if you multiplied two things with the same basis. We say 2 to the m over 2 to the n is always equal to 2 to the m minus n. And I think that what I want to do is I want to generalize this. So what we're going to do is we're going to go over here and look at the properties of exponents and then leave this video off here. But we say the two properties we just saw here were the product property, okay, the product property and the quotient property. And sorry I put them so far apart, but in general we say two things with the same bases, if you multiply them, so a to the mth power times a to the nth power is a to the m plus n, where the base stays the same base. You know, maybe we mark this in here. And same thing down here, same base. But when you divide two things with the same bases, you subtract their exponents. And this is how we're going to carry things out. The only other properties I want to really take the moment to discuss here are the power to a power property and a power of a product property, okay? We'll take a look at these two. We say a to the m, this being all carried to the nth, this would be the equivalent of saying like 2 to the third, and we take that to the second power. Because this time our base is all of this, we really mean 2 to the third power times itself twice, which we already know multiplying two things with the same basis, I can add these exponents. I get 2 to the sixth. But really what we could have done is we could have said, well, if this is the third power and that happens twice, I could really take 2 times 3 and get what we get here. So this power to a power property says when you take a power to a higher power, we can just go ahead and multiply these two powers together, okay? And then power of a product property, ab to the m, is a to the m, b to the m. It just means if I were multiplying a bunch of stuff like 2 squared times 3 to the fourth, and I take this all to the fifth, this power property, power to a power, gets extended, and I can see that as long as it's a product or a quotient right here, so multiply or divide, I can do this. I can say 2 to the 2 times 5 is 10, and then 3 to the 4 times 5 is 20, 3 to the 20. And this would mean the same thing without having to write everything out, okay? So when you look at the power of a quotient property, power of a quotient is the same thing as power of a product. It just says that everything in this quotient gets taken to this exponent here. Gets taken to this exponent here, okay? So the last two we want to visit are these two. We say the zero exponent property. The zero exponent property basically lays out the fact that anything to the zero power will always be equal to 1. There's only one thing we do not carry out to the zero power, and that's 0 to the 0. And then last but not least, our negative exponent property. Now what I want to call this is the move it property. Move it. And the reason why is because this. We say a to the negative m is what this says over 1. We can put everything over a negative 1 or over a 1. That's always fine. But you notice that this expression right here is just the reciprocal of the original expression, except for the m is now positive. So essentially what I can tell you is this. When you have a bar on a fraction, let's say a to the m over 1, and I take the base here, like I take this base and I stash it in the basement. We're moving it, okay? There'd be nothing left on top but a 1, but the moment I move this down here, what happens is you flip the sign on the exponent. So this could mean that I have an expression like 2 to the second times 3 to the negative fourth. And this is all over 1. What this means is I could take this base right here to make the exponent positive. I could just take it and stick it downstairs. We say 3 to the not negative 4 anymore, it'd be 3 to the positive 4. And we could certainly move this 2 down here and notice what happens to it. We'd say we get 2 to the negative 2 now, and 3 would be the positive 4. We tend to prefer to have positive exponents though. But these are our properties of exponents. In the next video we're going to move on to how each of these kind of plays into simplifying expressions. Cheers.